Welcome back, and in these short videos we're going to be looking at the amino acids and proteins pack. So we're going to be looking at the amino acids. We're also going to be looking at how we put them together to make di and tripeptides, and how we can join them together to make proteins. Also in this topic we're going to be looking at polymers, both polyesters and polyamides. So it would be useful if you could remind yourself of those two functional groups. So the amino acid functional group looks like this. We have an end here which is an amine functional group, and we have this group here which is a carboxylic acid functional group. The difference between the different amino acids is determined by this R group here. So this is my alpha carbon, and it always has these two functional groups on it and this R group. So if we take the simplest of the amino acids, glycine, you can see here my R group is a hydrogen. So you can see there the rest of the amino acids, and the only difference each time is this R group attached to the middle carbon. The amine group and the carboxylic acid functional group are always constant. It's only this R group which is changing, and that's what will give the different amino acids their different characteristics. So if it's got a very hydrophobic group, that will impact on the chemistry. If it has a polar group, that will also impact on the chemistry. Because the amino acids contain both the basic amine functional group and the acidic carboxylic acid functional group, they can act like an acid and a base. And in fact, at a particular pH, which is usually around about 7, they can form this Zwitter ion structure, where the nitrogen group has accepted a proton, accepted a hydrogen ion, and the carboxylic acid functional group has lost a hydrogen ion. Now the pH where this happens is generally around about 7. It will vary slightly depending on the nature of this R group here. But this does mean that amino acids have some characteristics which are not typical of organic molecules and are more typical of ionic compounds. The reason for this is these Zwitter ions can actually form ionic interactions. So they have a higher melting point than you would expect. They also, generally speaking, are soluble in water. Again, the R group will come into play. If that R group is very hydrophobic, that will reduce the solubility in water. If it's very hydrophilic, it will increase the solubility in water. At low pHs, where there is a high concentration of hydrogen ions, everything which could accept a hydrogen ion has done. So this amine group has accepted a hydrogen ion. The COOH group still has its hydrogen ion attached. Obviously, if this R group was basic and could accept a hydrogen ion, it would have accepted one as well. At our isoelectric point, as we said before, that's around about 7, depending on the R group, you've got both the positive end and the negative end. At much higher pHs, where there's a lack of hydrogen ions, everything which could have lost a hydrogen ion has done so. So this group is reverted to my amine, and I've lost the hydrogen from my carboxylic acid functional group. So at low pHs, the amino acid can act as an acid. An acid is something which can donate protons. Well, we've got a proton from here we can donate, and a proton from here we can donate. We may even have a proton on that R group which we can donate. So at low pHs, the amino acid can donate a proton. And that's what's meant by an acid. The pH at which amino acids can act as a nucleophile is a high pH. A nucleophile, if you remember, is a species with a lone pair of electrons. And at low pHs, here, this nitrogen group has already accepted a hydrogen ion, so it doesn't have any lone pairs it can use to accept anything else. And at this point, it does have a lone pair on the nitrogen. So at high pH, the nitrogen's lone pair is available. So amino acids exhibit what we call amphoteric behaviour. They can both gain and lose hydrogen ions. So they can gain hydrogen ions to form this species, they can lose hydrogen ions to form this species. And that's what makes them a buffer. A buffer is a solution that resists changes to pH on additions of small amount of acid or alkali. And we're going to be looking at their buffering ability in the little practical which is coming up next.
Okay, so this is just a little practical looking at the buffering action of the amino acids. So we're on page 4 of your notes, and I have 2 beakers, one containing a dilute solution of hydrochloric acid and the other containing my buffer. Now I'm going to add a small amount of sodium hydroxide solution to each. So if I add a couple of drops to this one, and a couple of drops to this one, and then I give each of them a swirl, so swirling that one, swirling that one. You can see there's very little colour change at the moment, but if I keep adding, I can add another 2 drops to this one. You should see that this one is starting to change colour. And again, another 2 drops, so I'm up to 6, and 6 in this one. And you can see definitely that this one, the hydrochloric acid, has changed colour, whereas the buffering solution, my amino acid, has not changed colour.
So that's the little experiment we did, and you can see there that for the amino acids the pH only changed gradually, whereas for the hydrochloric acid solution it changed sharply. And the type of behaviour we're seeing there for the amino acid is this buffering action. We're going to study buffers in more detail when we look at the acids and bases pack later on in the year. But you need to understand that buffering basically means that the solution resists changes to pH on addition of small amounts of acid or alkali. So if we look at the reaction of glycine both with hydrochloric acid and with sodium hydroxide. So if we start with glycine as the middle molecule, if you like, and it's the simplest one, so our group is just a hydrogen. Now if I added some hydroxide ions, they would react with this end of the molecule. So at high pHs, the nitrogen group has got no hydrogens to accept, but the oxygen of the COOH group has lost its hydrogen. But likewise, I can go the other way by adding hydrochloric acid, and this time it is the carboxylic acid functional group which is left alone, because it isn't going to lose that hydrogen, but the nitrogen group, which is going to gain a hydrogen and become positively charged. And you've probably got a chloride ion floating around there, just as you would have a sodium ion here. So these reactions are obviously reversible by just adding a bit of acid or a bit of alkali. So in this way it acts as a buffer, because it can react with a small amount of HCl and a small amount of OH negative, and the pH will remain roughly constant. So not only do amino acids act as buffers, they are all, with the exception of glycine, are optically active. And that's because the carbon, the alpha carbon, the carbon of the amino acid, has 4 different groups around them, so they'll form non-superimposable mirror images, because this carbon in the middle is chiral. So with the exception of glycine, where the R group is a hydrogen rather than a CH3 group or anything else, they're all optically active. They can all rotate the plane of plane polarized light. And this has important consequences for biochemistry, because you have 2 different versions of the same amino acid. So these amino acids can be joined together to make peptides. We can join them together to make even longer chains then, to make polypeptides and then proteins. Now as chemists we call the link between these amino acids an amide link because you're making an amide functional group. In biology you would call it a peptide link. But let's look at two simple amino acids and join them together to make a dipeptide. So I've got glycine and alanine. So if I start with one of these molecules, doesn't matter which one, I have my central carbon, I have my hydrogen. In this case I'm going to stick my nitrogen group on this end. The carboxylic acid functional group here has made a peptide link, an amide link, with the amine of an adjacent amino acid. So I have my carbon, and then in this case it's my C double bond O, which is not reacted. So I've got these two carbons here which are missing their R groups. So if I make this one glycine, that has a hydrogen on it, and this one aniline with a CH3 group on it, and there in the middle is my amide link. Now this backbone, if you like, is going to be the same no matter which amino acids I join together. The only difference is going to be these R groups. So the other molecule we've made is a molecule of water, and that's why these are often called condensation reactions or condensation polymers, because you've eliminated a small molecule of water. Now I'm going to do exactly the same but for valine and phenylalanine. So again I'm going to do the same thing I did before. I've got my backbone, C double bond O. This group has got my NH2 group on it, joined to my nitrogen group, should be a nitrogen, carbon with the hydrogen on it. In this case it's the C double bond O group. And then I have my two R groups. I've got vanillin, which is going to be, use a red pen here so it's different. So I've got a C, an H, and I've got a CH3 and also CH3 group there. And I've got on this one, I've got a carbon with my two hydrogens, and that's joined on to my benzene ring there. So that's valine and phenylalanine joined together, and I've got to put another hydrogen on that nitrogen group, and then again I've got my amide link there. So joining them together is a condensation reaction, but we can also break them up using a hydrolysis reaction. And they will break in the same place that they joined together. So they will break across this amide link. So they'll break back up into their different amino acids. And it's one of the ways we can work out what amino acids are present in a protein. We can hydrolyze the amide links, and then we can analyze the different amino acids. So it does take a while. You need to heat it under reflux with concentrated hydrochloric acid for quite a long time because this is quite a strong link. And then I will get my two separate amino acids. So there you can see I've broken them up into the two different amino acids. They've still got this NH3 positive group because it's in acidic conditions. But all I need to do is to add some water and I can get the different amino acids. And I can see here I've got a molecule of glycine and one of aniline. So I know my dipeptide is made up of those two amino acids. If I had a longer protein chain, I could do this and then analyze the resulting amino acid mixture to see which different amino acids made up my protein chain. So that finishes this first video, just looking at the amino acids and their reactions. So you should be able to identify an amino acid functional group. You should be able to react that functional group with acids and bases. You should be able to explain why they have a higher melting point and a higher solubility than you might generally expect from an organic molecule. You should be able to join amino acids together to make dipeptides and tripeptides, and you should be able to break them apart using hydrolysis. In the next video, we're going to move on and look at polymers.